100. I'm Professor Curtis, and this is the lecture for Chapter 34, Nuclear Fission and Fusion. Let's get started. This all starts with a guy known as Albert Einstein. So in one miracle year, 1905, Einstein published 4 groundbreaking papers, and this really propelled Einstein to superstar status in the world of physics. In the last of those 4 papers, he presented his best known equation. We'll actually talk about each of those 4 papers in a future lecture, but for right now, we're just going to focus on that last one where he presents his most famous equation, which is E equals mc squared. Mathematically, this equation says that energy and mass are equivalent. So E is the amount of energy you have, m is the mass, c is, of course, it's the speed of light. So the thing that's so groundbreaking about this is what the equation means conceptually. Mass and energy are equivalent. So remember before when we were talking about energy, and we said that energy cannot be created or destroyed? Well, you can say the same thing about mass. Mass cannot be created or destroyed because here energy and mass are equivalent. And remember before when we said that energy can be transformed into different types of energy? Well, mass, because it's the same as energy, is just another form of energy that energy can be transformed into. And what ties all of these equivalencies together is the speed of light. So, on the atomic level, this equation upholds the conservation of both mass and energy by accounting for all the mass and energy of nuclear reactions. Okay? And this is what we see with nuclear reactions, because when things decay, okay, you've got less mass. So where did the mass go? Well, the mass has to be accounted for somewhere, and the mass is accounted for because it gets transformed into energy. And this is how nuclear power works. We're basically taking the decay of matter where the mass is lowered, and that lower mass is then, the difference in the mass has been transformed into an increase in energy so that everything balances out. So here's your basic process when you're dealing with nuclear fission. Nuclear fission meaning you've got particles that are separating themselves at the nuclear level. So typically we're going to start with U-235. So this is uranium isotope, and its atomic weight is 235. This isotope of uranium is going to absorb a neutron. Okay, and when it does this, okay, the nucleus becomes elongated because now you've got a little extra particle that's there in the nucleus. Okay, so you've got all these, nucleons crowding around, and another one joins the party. So then, what was standing room only now becomes, even squished standing room only. Well, at this point, electrical forces overcome the strong force. So everything then starts to break apart because those electrical forces, the light particles, are going to repel each other, and the nucleus separates into 2 smaller particles. So you start off with U-235, and it basically separates into krypton 91 and barium 142. There are 3 neutrons that come out of that separation. So those neutrons, okay, then basically are colliding with other U-235 nuclei, and they then split off, and so it's a chain reaction. So the more this keeps going, the more you get, it just grows and grows and grows and gets bigger and bigger and bigger. And so you get a basic chain reaction going. And that's the way nuclear fission works. Okay? Now the mass of the original uranium nucleus is greater than the combined mass of the krypton and the barium and the neutrons that come off. So, mass has to be conserved just like energy. So where did that difference in mass go? Where's that missing mass go? Well, it goes into the energy that you get out of the nuclear reaction. And the energy that you get is equal to mc squared. So that missing mass times the speed of light squared gives you the amount of energy that you get from the reaction. And this is the way nuclear fission works. Here's a basic setup for how the nuclear fission reactors are going. So you've basically got control rods that are there that can be inserted in between fuel rods. So the fuel rods are where we're keeping the U-235, and you've got control rods that come in the middle there. And what the control rods are doing is they're basically composed of a material, and usually it's something like graphite, but there are other materials that work as well. And you basically want to absorb those neutrons that get split off when you get the fission of the two into the two atoms. So, something that absorbs, because if you don't absorb those neutrons, then they just keep growing and growing and growing and multiplying, and the reaction just gets really out of hand. So you got to be able to control that. The way we control that is with control rods. So we slip the control rods in there between the fuel rods, and then they absorb those excess neutrons and everything calms down. When we remove the control rods, then that basically, lets the reaction keep going and going. Well, this reaction, of course, energy is being produced, and most of that energy is in the form of heat. So heat is going to warm the water that's around the fuel rods, and there's pumps that pump that water out, and we basically pump that water out, and then we use that to heat water that's in the heat exchanger. We want to keep those two systems separate because the water that's in direct contact with the fuel rods becomes irradiated. So in order to contain the radiation, we keep that first system of water, pretty much contained, and then it heats the second form, which doesn't get irradiated as much, and then that water is heated to form steam. Steam then turns a turbine, which then turns a generator. And of course, you've got all the magnets that are turning there inside the generator. It induces electric current, which is then pumped out onto the grid. So that's the basic way this works. Notice there's four main components to the nuclear fission reactor. The first is the nuclear fuel. That's the fuel rods. The second, you've got the control rods, so you can control the nuclear reaction. Then you've got what's called a moderator, which is basically the containment unit for the fuel rods. And then you've got the heat extracting fluid to take the heat out from the nuclear reaction so that we can then do usable work with it. These are the four main components for your nuclear fission reactor. This brings us to the concept of mass per nucleon. So if we take a look at each of the different elements and we organize them by atomic number, and then we take, how much mass do we have per nucleon? So, helium is going to have the highest mass per nucleon because you've got the mass of 1 proton and 1 neutron. That's the nucleus of a hydrogen atom. And you're going to divide that by how many nucleons do you have? You got 2. So you divide that by 2. You move on to helium. You've got 2 protons, 2 neutrons. Now you're dividing everything by 4. So everything gets a little bit lower. And then you move on to the next one, which is lithium. So now you've got, 3 protons, but I think you've got like 6 neutrons. So then you're dividing, that total mass by 8. So it just keeps going. You just keep dividing by a bigger number until you get to iron. Iron is the low point of the graph. And then after iron, things start to pick up a little bit. But you notice that it doesn't pick up anywhere near to the levels that you get with hydrogen. So with hydrogen, we've got, if we move closer to iron, the mass per nucleon is going to get reduced when we separate things out. So, fusion, if we put things together, so we've got smaller elements and we're putting them together to make bigger elements. So that process is going to reduce the ratio of mass to nucleon. So we go, and that's shown by the graph. When you go down the graph, notice we're getting lower. So the mass per nucleon is lower as we go from hydrogen to iron. So if we take 2 small nuclei and we fuse them together, the mass of the fused nucleus is actually going to be less than the mass of the two single nuclei that happened before we fuse them together. Well, again, there's that difference in mass. So how do we account for the difference in mass? Well, the missing mass is it comes in the form of energy from fusing the two smaller elements together. Notice we get the same thing if we go the other way. Okay, so if we've got uranium there on the far end, this is where most of our fission reactions come from. So fission is going to take these larger atoms and separate them out into smaller ones. So that means we're going to get closer to iron. And so, our graph is going down. So again, we see a reduction in the mass per nucleon. So whether you're looking at fusion or fission, okay, the mass per nucleon is going to go down, but the bottom there of your graph is iron. Iron, kind of interesting that iron would be the low point of your graph, since iron, main constituent for steel, which is the most common engineering material that we have. Lots of things are built with steel, so it's kind of interesting that iron would be they're the low point of your graph, but that's the way the math works out. There's basically two types of fusion reactors. The first is what we call a magnetic confinement fusion reactor. And basically you've got magnetic fields, okay, that confine the nuclei of these atoms together, that basically, and the magnetic forces are basically pushing the atoms together. So that's why it's called magnetic confinement, because the atoms are confined within this magnetic field that pushes them together and causes them to fuse. The other type of fusion reactor is called inertial confinement, and this is basically where you've got particles from different streams that are basically thrown together. Okay, so it's the inertia from the momentum from those moving particles that are causing them to fuse together, and that's why it's called inertial confinement. So two basic ideas there for fusing particles together, but neither of these types of reactors are very economical. They're not very cost effective. And so that's why most commercial nuclear reactors are going to be using fission and not fusion to produce energy. Let's take a look here at an activity involving the concepts we just learned about. So take a moment to stop the video, and then in your workbook, go ahead and answer the 4 questions that you see here on the screen. And then when you get done with that, come on back and we'll see how well you did. Okay, let's see how well you did with this. So we've got 4 questions here. And so the first question is, what element do you typically think of when you hear nuclear fission? Well, there's different ways you could have answered this question. Okay, lots of people think about uranium, plutonium, but there's also thorium, radium, radon. There's many different answers you could have given in response to that question. But no matter what you answered for the first question, the second question, where are those elements located on the graph? Well, they're going to be located on the far right, okay, towards uranium. See, on the far right, you've got uranium. So notice you're maximizing your distance away from iron. That's where those elements are located. Now, why is it that those elements are used? Why don't we use elements that are closer to iron? Well, the reason being is that the farther away you get from iron, the more mass per nucleon you have, and so the more mass you'll have missing when you do your nuclear reaction, which then translates into more energy. So the further away you get from iron, the more energy you get that's produced. It's the same way on the flip side. Okay, so for question number 4, what elements do you think are the best for nuclear fusion? You're going to be taking the lightest elements. So elements like hydrogen and helium are used in fusion reactions because, again, they're the furthest away from iron. So the reason why we want to get away from iron is because if you look at your graph, iron is the lowest point on the graph. So we want to get away from iron because that's the low point. That's where the energy we get is going to be minimized. If we want to maximize the energy, then we want to get to the higher points on the graph, and so we got to get as far away from iron as we can get. And that's why for fission, we use the heaviest elements that we can find, which are around uranium. And then for fusion, we use the lightest elements that we can find, which are like hydrogen and helium, because these are the furthest away from iron. And that brings us to the end of this lecture. Hope you found this video helpful. Thanks for watching, and we will see you in the next video.